This is part 5 of the rates and equilibrium topic. It's an AQA GCSE chemistry topic, and it's valid for dual and triple award students. As always, I'm going to recommend you pause and try the activities before review. In this video, we're going to take a look at catalysts. We need to know what a catalyst is, and we need to know why they are important for industry. Now, as a reminder, we have already in previous videos looked at the impact of increasing surface area, temperature, concentration and pressure, and we need to be familiar with all of those. Catalysts are the final form of, or the final method of increasing rate of reaction that we are going to look at. I'm going to give you a series of questions for you to have a think about and see how effectively you could answer them. So, what is a catalyst? And there is a standard definition for this one. And what we're looking for is that a catalyst will speed up the rate of a reaction, but it is not used up in the reaction. So we've got two specific points there to include. Now, we might also want to consider how a catalyst works, but we mustn't get these mixed up. This or these 2 points are the definition, but the way that it works is that it lowers the activation energy. Spoke about activation energy back in the energetics topic, and it does that by providing an alternative reaction pathway. Next question. What impact does a catalyst have on the rate of a reaction? Well, the definition has told us this. It will increase the rate of reaction. A little bit of a reminder of an old topic here. We're going to look at an energy profile diagram and then use that to show what impact adding a catalyst has. So let's start by drawing out the axes and labelling them. We've got energy and progress of reaction. I'm going to add my reactants on the left hand side. That's how much energy they have. And this is an exothermic reaction, so the products will have less energy than the reactants. And that's because this is the energy change. This energy has been released into the surroundings. But we spoke in previous videos about the fact that I can take methane and put it in a container with oxygen and it doesn't react. It needs a spark. It needs activation energy. And that's represented by the hump that we can see here. And the activation energy I have labelled. I have to put this much energy in so that we can theoretically break all of the bonds in the reactants to then make all of the bonds in the products. That fits in with the bond energy calculations at the end of the previous chapter. So what will happen if we add a catalyst? Well, I explained earlier in the video that a catalyst will lower the activation energy. So it brings the hump down. You can see here that with a catalyst, the activation energy is much lower than without a catalyst. That means that more particles will have energy equal to or greater than the activation energy, so their collisions are more likely to result in a reaction, so the rate increases. Next question. So there are lots and lots of examples. I've got 3 here that I will talk through. You will get more familiar with these as you get through the remainder of the GCSE course. Iron is used in the Haber process. The Haber process is coming up actually later in this topic, and it relates to the manufacture of ammonia. We also use nickel in the hydrogenation of alkenes. And platinum is a catalyst used in catalytic converters, which are present in a vast majority of cars nowadays. Next question. And catalyst poisoning is important, and that's because catalysts do sometimes have to be replaced. But what actually is it? This is when impurities start to build up and those impurities start to combine with the catalyst. It means the catalyst can't work anymore. The catalyst stops working, it stops speeding up the reaction. So you take the catalyst away, you remove the impurities, and then you replace the catalyst, and we go back to the lower activation energy that we were benefiting from. So we're also going to take a look at a practical that relates to catalysts, and we've got lots of information here that you can read through and some questions for you to try. So have a go at this equation. And it does tell you that hydrogen peroxide is H2O2. It tells us we're making H2O and water. So I've got my H2O2, I've got my H2O, I'm making oxygen, and I've got to remember that oxygen is a diatomic element. It exists as an element in pairs of atoms. Others that do that: hydrogen, nitrogen, oxygen, fluorine, chlorine, bromine, iodine, astatine. Have a look at where they are on the periodic table and you will see a very, very clear pattern. They are in a number 7 shape on the right hand side of the table. If you want another way to remember which elements exist diatomically, it's H-NOF-Cul-Briat. H-NOF-Cul-Briat spells out the symbols of the elements that exist diatomically. I need to balance this now because I've got 2 oxygens and 3 oxygens. I'm going to need to balance by adding a 2 here and a 2 here. The catalyst itself, the method itself is we're going to take hydrogen peroxide. We are going to measure the oxygen, the volume of oxygen given off, and we're going to measure how long it takes to make 25 centimetre cubed of oxygen. Now, you've seen measuring the gas syringes in previous videos in this topic, so I'm not going to put a diagram up again, but we're going to look at a series of potential catalysts. And we're going to see how long it takes to make the measured amount of oxygen. And I'm going to put some data in, and we can see here that we've got some that took a lot longer than others. Potassium iodide was quite fast, magnesium dioxide was even faster. So let's think about some questions that go with this. Which was the most effective catalyst for the reaction, and why did you choose it? Well, taking a look at the table again, it's magnesium oxide. That had the greatest impact on increasing the rate of reaction. It was the fastest that the reaction took place, so it increased the rate of reaction most. Was the experiment a fair test? Now, fair test is not a term we commonly use, but let's have a look at what would make it fair, what would give us valid results. And actually, there's a lot that says we would. We used the same mass of catalyst each time, we used the same volume of H2O2 each time, and we collected the same volume of O2 each time. All 3 of those are control variables, and we did control them. How could we improve it? Well, we could try to control the temperature, but that's not always possible in a lab. But another really good way of doing it is to take repeat readings. Why not do the experiment 3 times with each catalyst? That allows you to identify and discard any anomalies, and you can then work out your averages, your means, and you've got data you can be far more secure with that you've got valid results. That takes us to the end of this video. Thank you for listening, and goodbye.